So in this video we are looking at the graph of y equals square root of x, so the square root function. So we're going to introduce the new graph shape. We're going to think about the transformations that we already know and understand in the context of this graph shape, but we actually have a need to think about two further transformations here. There's actually two transformations missing from the set of transformations that we've thought about so far. So we need to, and we haven't needed them in other graph shapes. They've been irrelevant, and we'll see why that is the case a little later on. But they become necessary in looking at this graph shape, so this is the time to introduce them. Okay, so our new graph shape, our graph is y equals square root of x, or y equals x to the power of a half. They are the same thing. Okay, let's think about some points. So when x is 0, obviously y, which is the square root of x, is the square root of 0, which is 0. So the graph goes through the origin. When x is 1, y is the square root of 1, which is 1. So it goes through the point 1, 1, which we can see. When x is 2, y equals root 2. Root 2 is about 1.4, I think. So that's what we're seeing there. When x is 3, y is root 3. I think which is about 1.6, maybe 1.7. Let me have a quick look. Root 3, yeah, 1.7. So that's fitting with what we're seeing there, the 0.3, 1.7. When x equals 4, y equals root 4, which is 2. We go through the 0.42. And we could continue. The next most obvious point is when x equals 9, y equals root 9, which is 3. And we've got that point happening up there. So here is our square root graph. Now, we know that the square root is the opposite or inverse operation to squaring, and in fact the square root graph is the inverse graph of a parabola, and we'll look in a lot more detail at inverse functions in our next topic. But when we talk about an inverse graph, so we know that the parabola looks like this. And an inverse graph is when we take that shape and we mirror it in the line y equals x, and in this case that means that we get this. Now there's a reason why when we're looking at the square root of x we only have the top half, and that's because when we take the square root of a positive number we get a positive number. There's also things to learn about when we look at inverse functions about what's going on there. But we are essentially looking in this shape here at a sideways half a sideways parabola. Okay, so in thinking about what the graph shape looks like, so there's no asymptote happening up here. This is not a graph that's approaching a particular value. Okay, this is a sideways parabola. We know the parabola keeps going on and on and on forever. Okay, it gets more and more, the parabola gets more and more steep, and so therefore this square root graph is getting less and less steep. Okay, so it's not becoming straight. It's just curving less and 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 less. Okay. So thinking about that when you draw the shape. So this is our basic shape. Okay, let's think about the transformations that we just one thing to note, so the square root graph only exists for x values where x is bigger than 0. So yeah, I didn't think about, alright, let me go back here for a second, sorry. So x, if x were to equal -1, y is the square root of -1, which is undefined in the real number system. Okay, when x is -2, y is the square root of -2, which is undefined. So we can't square root a negative value, and so the graph of the square root of x doesn't exist at all to the left of the y-axis. Okay, so that's really important. Also, y equals the square root of x only exists for positive y values when y is bigger than 0, bigger than or equal to 0. Sorry, it does go through the origin. Okay, let's think about our transformations that we already know about. Let's just have an exploration of that in a graphing package for a second, things we already know. So first thing to note here is at the moment I'm looking at the graph of y equals the square root of x. I've got a red graph here which is actually sitting underneath that black graph, and we'll adjust it, which is a more complicated version of the equation. It is a times the square root of n times x minus h plus k. Now for now we haven't thought about n at all, and that's where I'm going to introduce that in a minute. So for now let's forget about n. Let's just think about the fact that we've got sorry, the pen functionality in this program is really poor. So square root of x minus h and then plus k. That's what we're dealing with there. Okay, so at the moment I've got a is 1, h is 0, and k is 0. We're forgetting n for a minute. And so we are just looking at the graph of y equals x, y equals square root of x. So let's think about A first. So we know that changing A is about dilating from the x-axis. So we would expect as we make A bigger, A is stretched away from the x-axis, which is exactly what we're seeing. Okay. If we were to go back and make A1, obviously our graph is exactly equal to square root of x. If we were to then make A smaller, so a fraction, the graph is squashed towards the x-axis, and that's because we're dilating by a factor that is less than 1. So we're multiplying all the y values by, at the moment, 0.5. Okay, so the graph is dilated by a factor of 0.5 from the x-axis, which means it's going to be squashed down towards the x-axis. If we keep making A smaller, obviously you're squashing it further and further. If A is 0, it's not a square root graph at all, it's just a straight line. And then when we get into negative territory, we now see that we've actually got two things happening. Our graph is reflected in the x-axis because of the negative, and we've got that dilation from the x-axis. Okay, so if A is -1, if we've got negative square root of x, we have the reflection in the x-axis. And obviously those two graphs together, positive square root of x and negative square root of x, they give us that full sideways parabola. And as I said, we'll revisit that in our next topic when we look in more detail at inverse functions. Okay, so A is behaving exactly as we would expect. Let's have a look at K's the next simpler one, so let's go straight to K. So K is when we add or subtract the number on the end, and we know that's about translating up or down. So increasing the value of K is going to translate the graph up, decreasing the value of K is going to translate the graph down. Okay? Alright, H, now we know H works a little backwards to what we're expecting, so we've got it written in the equation as x minus H. So I know if I make H 1, oh sorry, here it is, 1, so I've now got the square root of x minus 1, and my graph has gone to the right by 1. X minus 2, my graph is square root of x minus 2, my graph's gone to the right by 2. Square root of x minus 4, my graph's gone to the right by 4. Square root of x plus 2, and my graph has now gone to the left by 2. Square root of x plus 5, and my graph has gone to the left by 5. Okay, so nothing different here, translating left and right, but when we have x plus a number, we go to the left, and when we have x minus a number, we go to the right. Okay, and that's obviously happening inside the function, so underneath the square root. Okay, so there's nothing unfamiliar with those things, so let's go back to our notes and fill in the things we're already comfortable with. So dilation by a factor of a from the x-axis is a times the function. So for the square root graph, that will be y equals a times the square root of x. Okay, so here we're looking at where f of x is root x. So a times f of x is a times root x. Reflection in the x-axis is where we make the whole function negative. So again, y equals -1 times the square root of x, so that is just negative root x. Translation to the right by h units is f of x minus h. Okay, so inside the function, just replacing the x part of the function with x minus h. Okay, so remembering how this function notation works, just the x is being replaced with x minus h, and so we're going to get square root of x minus h underneath the square root. So that goes to the right by h units. And then translation up by k, f of x plus k. So f of x is square root of x, and then separate to that, adding on k. Okay, so again, being clear about that difference between the translations left and right and the translations up and down. And obviously then we can combine all those things together. So we can have a, which could be dilation or reflection, dilation and or reflection I should say, square root of x minus h, translation left or right, plus k, translation up and down. Okay, so before we move on, we're missing two transformations here out of the set. So let's think about what happens here. So when we dilate from the x-axis, this is all the y coordinates. So we multiply the y coordinates by a. That's what happens. Okay, we stretch away from the x-axis, the y coordinates get multiplied. We reflect in the x-axis is that we multiply the y coordinates, all the y coordinates of the point on the graph, by -1. And that reflects it in the x-axis. All the y values become negative, the graph ends up upside down. Translation to the right by h units, okay, we add h onto all the x coordinates, okay, and that moves the whole graph to the right by h units. Translation up by k, we add k onto all the y coordinates. Okay, now I'm not talking about what's happening to the function, I'm talking about what's happening to every single point on the graph. So if we go back to our graph here, and I take it, and I take it to the left by 2, that is because, okay, the equation is y equals square root of x plus 2, but what has happened to every single point on this graph is we have subtracted 2 from the x coordinate in order to move it to the left by 2. Okay, so if we're moving to the right by 2, we would be adding to move to the right, onto all the x coordinates to move to the right by 2. As I said, I'm talking about the x coordinates, not about what that looks like in the equation of the graph. Okay, and then all those things are combined. So if we think about what's happened here, we've looked at adding and subtracting onto x or y coordinates. But here, we've only looked at what happens when we multiply the y coordinates, so stretching away from the x-axis, and what happens when we make the y coordinates negative, so reflecting in the x-axis. What we haven't considered is what about if we multiply the x coordinates by something, so we stretch away from the y-axis. And what about if we make the x coordinates negative, so we reflect in the y-axis? Those are the two things that are missing. We want to have a look at those now before we move on to sketching some graphs. Okay, so the first thing we want to think about is reflection in the y-axis, okay? And as I said, we are already familiar with our reflection in the x-axis. It is when we have negative f of x. So for our square root graph, that is negative square root of x. Reflecting in the y-axis is when the x part of the function is made negative, not the whole function, as in the x-axis reflection, but the x part of the function is made negative, which makes sense given that what's happening if we're reflecting in the y-axis is that we're making the y coordinates negative. Okay, so for our square root graph, that means, again, replacing, like we did before, replacing the x values in the function. So remember, thinking about the fact that this is, sorry, let me write, I should have written this out first. What we're saying here is that f of x is equal to the square root of x. So what we're looking at here is replacing all the x's in the function with negative x. Okay, so my equation becomes square root of negative x. People go, oh, that's an issue because you can't square root a negative. But the whole point is that yes, when x equals 2, this function's not defined. Okay, because that would mean square root of negative 2. But when x equals negative 2, square root of negative 2, this function is defined, okay? So it's just going to change where it is. And we can also think about that because it's reflecting this graph shape in the y-axis. So I'll come back to that once we've drawn it. So here we've got y equals root x. I want to sketch these 3 graphs, which is dealing with all the reflections that we could have. So y equals negative x squared is reflection in the x-axis. That's the one we already know about. So we take each point. This point at 1, 1 moves to 1, negative 1. This point at 2, root 2 moves to 2, negative root 2. This point at 3, root 3 moves to 3, negative root 3. This point at 4, 2 moves to 4, negative 2. 9, 3 moves to 9, negative 3. Okay, and we get the mirror image reflected in the x-axis. Okay, so we've got, sorry, I moved the mouse. So y equals negative square root of x. We're familiar with that one. Okay, then let's think about, I'll draw it in a different colour. Let's think about this one. So y equals square root of negative x. So that is a reflection in the y-axis. So what that means is every point, the x value is going to become negative. So this point at 1, 1 is going to come over here to negative 1, 1. This point at 2, root 2 is going to come over here to negative 2, root 2. This point at 3, root 3 is going to become 3, negative root 3. 4, 2, sorry, I've written the wrong way around. Sorry, 1, 1 goes to negative 1, 1. 2, root 2 goes to negative 2, root 2. 3, root 3 goes to negative 3, root 3. 4, 2 goes to negative 4, 2. 9, 3 goes to negative 9, 3. Okay, and we get the whole graph shape reflected in the y-axis so that it's happening over here. Okay, so you can see, coming back to that point of, oh, but I can't take the square root of a negative. Yep, that's fine. That's why the green graph, doesn't exist over here. okay? Because when x equals a positive number, you will be trying to square root a negative number, and therefore that's not possible. But it does exist over here with the negative numbers. And that's because, for example, when x equals negative 9, y equals square root of negative 9 is square root of 9, which is 3. And that's how we get that point up there, okay? Alright, the third graph I want to draw on here is this one. Let me find another colour. So this one here. So we've got the negative out the front and the negative inside. So we're going to be doing both reflections. So reflect in the x and y axes. And when we do that, both the x coordinate and the y coordinate become negative. So the point 1, 1 becomes the point negative 1, negative 1. The point 2 root 2 becomes the point negative 2, negative root 2. The point 3 root 3 becomes the point negative 3, negative root 3. Negative 4, negative 2. Negative 9, negative 3. Okay, and we get this graph out here that is reflected in both the x and y axes. Okay, so that's the first thing. Sorry, I should have labelled this one. That's the first thing you need to think about when you're sketching a square root graph, and I'll come back to that in a minute. That you need to first of all think about the reflections to work out which of these 4 shapes are you dealing with. The red shape, the blue shape, the green shape, or the purple shape. Okay, so the next transformation that we haven't thought about is, before we move on to that, is the reason that we haven't thought about reflection in the y-axis until now, okay, is because it actually hasn't been relevant to all of our previous graph shapes. So let's have a think about the graph shapes that we've got here. So if I draw the graph of, if I reflect each of these graphs in the y-axis, so y equals x, this is what it's going to look like when I reflect it in the y-axis, okay? We know reflection in the y-axis is when y equals f of x becomes, is when y equals f of x becomes y equals f of negative x. So the x part is made negative. And so that means the equation of this, if I've replaced the x in that equation with negative x, I get y equals negative x. Now that's just the same as negative f of x. It's the same as the reflection, in the x-axis. So we already know how to reflect a graph in the x-axis, and for the straight line, that gives me the same thing as if I reflected in the y-axis. So I don't need to understand y-axis reflection when I'm dealing with linear graphs. Okay, we can always think about them as x-axis reflections. Similarly, the parabola. If I reflect the parabola in the y-axis, what happens? Well, absolutely nothing happens because it's a graph that's symmetric about the y-axis. So again, thinking about this idea up here, if you take y equals x squared and reflect it in the y-axis, you get y equals negative x squared, which is just y equals x squared. So what you find here is that f of negative x is f of x, okay? Whereas in this one, f of negative x gave you negative f of x. So in the first example, the linear graph, the reflection in the y-axis was the same as the reflection in the x-axis. In the second graph, the parabola, the reflection in the y-axis is just the same as the original graph, so no reflection. So therefore, it wasn't relevant to think about in the context of the parabola. Let's think about the cubic. We reflect the cubic in the y-axis, so flipping my points across the y-axis, I get this graph happening, which again, so reflecting it in the y-axis is the same as if I had reflected it in the x-axis. And again, the algebra of that, y equals negative x all cubed, is the same as negative x cubed. Okay, so what we see here is f of negative x is the same as negative f of x. So the reflection in y is the same as the reflection in x for the cubic. Okay. The quartic, you reflect that graph in the y-axis and you get exactly the same graph. So just like the quadratic, the parabola, okay, y equals negative x to the power of 4 is the same as x to the power of 4. So we find that f of negative x, the reflection in the y-axis, just equals f of x. It doesn't actually change the graph at all. So again, we didn't need to think about reflecting in the y-axis for the quartic. The hyperbola, which we introduced last lesson, if we reflected in the y-axis, so again, moving all our points over this way, we find the branch that's in the top right is going to move over to the top left, and the branch that's at the bottom left is going to move to the bottom right. But it gives me the same result as if I had reflected it in the x-axis. Okay, and again, thinking about your equation, it's 1 on x, you replace the x with a negative, 1 on negative x is the same as negative 1 on x. Okay, so again, f of negative x is the same as negative f of x. Okay, so that is reflection in the y-axis, same as the reflection in the x-axis for that particular function. And the last graph shape we've looked at in terms of all our transformations is the truncus. And if I reflect the truncus in the line y equals x, it's symmetric about, sorry, in the y-axis, it's symmetric about the y-axis, and so I get the same equation. So again, y equals 1 over negative x all squared, reflecting the truncus in the y-axis, is just the same as 1 on x squared. So reflection in the y-axis is just the same as the original function. So reflecting in the y-axis hasn't been necessary up until this point. It either produces the same graph we get by reflecting in the x-axis, so we can just think about reflecting in the x-axis, or it didn't make any change. The square root graph is the first time where we actually get a completely different graph that doesn't equal the original graph and that isn't the same as the reflection in the x-axis. And so this is the first time we need to think about this as a different and separate transformation, the reflection in the y-axis. There'll be other graphs that we introduce later this semester when we look at the exponential graph. Reflecting that in the y-axis will be different. Looking at the log graph, when we look at that later this semester, that's also going to be important to be able to reflect it in the y-axis. And next semester, when we start to look at our graphs of circular functions, we can also think about reflecting those in the y-axis, although actually we can again narrow it down to always just thinking about reflection in the x-axis when we look at those graphs. But again, this is going to become necessary as we move forward. Okay, so reflection in the y-axis was one of the missing transformations. The other missing transformation was dilation from the y-axis. Okay. Now, before we get into filling in this table and having a look here, again, I want to have a play with the graphing program. Okay, so we're back over here in the graph, and so now I want to focus on n. Forgot to use my pencil. This number in here, so underneath the square root. Okay, so we really just want to focus on y equals the square root of nx. I'm going to leave all the other variables as, I'm going to leave a as 1, so we just have 1 times the square root, and I'm going to leave h and k as 0, so there's no translation. So we just want to focus on that value there, n, what happens as we change n. So I'm going to, in my constant controller down here, I'm going to look at n. I've also marked a point on the two graphs so that you can get a clearer sense of what's moving where as this happens, because it can be sort of hard to see, and it's sort of hard for me to draw on this particular screen, which is a bit annoying. So if I make n bigger here, so I'm going to make n larger, so currently n is 1, so it's a square root of 1 times x. If I make n larger, remember what we're looking at is the dilation relative to the y-axis here. So as n is made bigger, what we see here is the graph gets squashed, not stretched. So it's opposite to what happens for the dilation from the x-axis. And it is again to do with the fact that n is under the square root. In the same way that what happens with h is opposite to what we think it should. We add on h, we go left, we subtract h, we go right. Okay. In the same way, n is also the opposite of what we think. So as we make n bigger, if we're looking at dilation from the y-axis, what is happening here is the graph is being squashed towards the y-axis. Okay, so the x-coordinates aren't being made bigger. The x-coordinates are being made smaller as we make n bigger. Okay, now with the decimal values, it can be sort of hard to see how the decimal values are being made smaller. So at the moment, for example, in fact, let me see if I make n 5, we might be able to see a bit more clearly. So when n is 5, so square root of 5x, the x-coordinate hasn't been multiplied by 5, the x-coordinate is now 0.2. So the x-coordinate has actually been divided by 5. if we again extend, let's go back to making n 1 and look at what happens when we make n smaller. So as we make n smaller, as I make n less than 1, 0.9, 0.8, 0.7, we find our graph is stretching away from the y-axis. The x-coordinates are getting bigger. So here's the first point that might help us to see what is happening. When n equals 0.5 or 1/2, the x value has been doubled. Okay, so we've stretched away from the y-axis by a factor of 2. Let's keep making n smaller. So when n is 1/3, no, sorry, it's 0.3, so it's a bit misleading. Let's go with this one. When n is 0.2, which is 1/5, the x-coordinate has been multiplied by 5. When n is 0.1, which is 1/10, the x-coordinate has been multiplied by 10. So it's all about the reciprocal of n, okay? When we have y equals the square root of nx, we are dilating from the y-axis by the reciprocal of n. Okay, remember reciprocal we've talked about before, negative reciprocal for gradients of perpendicular lines, it's when you flip the fraction upside down. So if n is 2, the reciprocal of 2 is 1/2. If n is 10, the reciprocal of 10 is 1/10. If n is 3/2, the reciprocal of that is 2/3. Okay. In fact, let's see if I can do that. If I can make n 1.5, which is 3/2, we can indeed see that the x-coordinate is 2/3 of the original x-coordinate. 0.6 recurring is 2/3. Okay, let's look at what happens when we make n negative, because that's going to combine together the two transformations we've just talked about. So if n is negative, if n is negative, sorry, I don't know. Oh, it's because I made the step so big. Sorry, let me make it. Go back here. Sorry, okay. So if I make n negative, we see here that we get, now we can make it smaller again. Okay, that we are both reflecting in the y-axis and dilating from the y-axis. Okay, but dilating from the y-axis by a factor of 1/n. So the negative, again, the negative value, that's the reflection, and the value of the number is about the dilation. Okay, let's go back over to our notes. So dilation from the y-axis, so comparing dilations from the y-axis with dilations from the x-axis. So again, thinking about that here, f of x is equal to square root of x. Dilation from the x-axis by a factor of a, we know that is just multiplying the whole function by a. Dilation from the y-axis by a factor of a is multiplying the x part of the function by the reciprocal of a. So in this case, that will be square root of 1/ax. Remembering we could also write that as x over a. That's a dilation by a factor of a from the y-axis. That would stretch the graph away from the y-axis. If we want to dilate the x-axis from the x-axis by a factor of 1/a, we would put 1/a out the front of the function. 1/a times x would dilate from the x-axis by 1/a, so it would squash down towards the x-axis. If we want to dilate by a factor of 1/a from the y-axis, it is going to be y equals f of ax. Okay, so it's the reciprocal when we're dilating from the y-axis. Sorry, reciprocal. Let's try that again. Reciprocal. Okay, so in this case, that would be y equals square root of ax. So if we have square root of 2x, that is a dilation by a factor of half from the y-axis. It gets squashed in towards the y-axis. Okay, so as I said, much like the translations left or right, the dilations from the y-axis don't occur as might be expected. We have to use the reciprocal. Again, we'll look at the algebra of why that happens next year. For now, we're just going to observe what we've seen with the graphs and seen that when we make n bigger, the graph squashes in. When we make n smaller, the graph stretches out. Okay, sketch the graphs of square root of 2x and square root of half x on the same set of axes. Okay, square root of 2x is a dilation by 1/2 from the y-axis. So that means all the x coordinates are going to be halved. So this point at 1, 1 goes to 1 half 1. This point at 4, 2 goes to 2, 2. This point at 9, 3 goes to 4 1/2, 3. Okay? So we're halving all of the x coordinates. So the graph gets closer to the y-axis. Okay, so it's about that. We're halving that way. If we're looking at y equals the square root of half x, which we could also write as square root of x on 2, that's a dilation by the reciprocal of half, which is 2 from the y-axis. So that's going to stretch the graph away from the y-axis. All the x coordinates are going to get doubled. So the point at 1, 1 goes to 2, 1. The point at 4, 2 goes to 8, 2. I might put a few others in. This point at 2 root 2 is going to go to 4 root 2. This point at 3 root 3 is going to go to 6 root 3. Okay, so again, this time we're doubling out this way. Okay, and we get the graph of y equals square root of x on 2, or half x. This one was y equals square root of 2x. Okay, so being clear about the difference between those two things. Alright, let's have a think about why we haven't had to think about this before now. So with the functions we've met so far, it has been possible with all of those functions to manipulate the function so that we only ever think about dilations from the x-axis. So for example, we now know that if we did y equals this brackets 2x all squared, that would be the graph of y equals x squared after a dilation by half from the y-axis. So you've replaced x with 2x, it's a dilation by half from the y-axis. But we know, algebraically, we can also write 2x squared as 4x squared. Okay, so we don't have any brackets. We don't actually need to think about it as a y dilation. So 4 times x squared would be a dilation from the x-axis by a factor of 4. So let's think about what happens there when we draw those graphs. So if we think about dilating the parabola from the y-axis by a factor of a half, this point at 1, 1 is going to go to half 1. This point at 2, 4 is going to go to 1, 4. This point at 3, 9 is going to go to 1 1/2, 9. This point at 4, 16 is going to go to 2, 16. And we would get the same mirror image happening on the left-hand side. Okay, so that is thinking about dilating by a factor of half from the y-axis. Okay, and we join that up and we get our parabola. That is y equals 2x all squared. But we could also think about dilating from the x-axis by a factor of 4. So the point 1, 1 goes to the point 1, 4. The point 2, 4 goes to the point 2, 16. The point, and we could do the same on the other side. We could pick some other points as well. So actually, they do produce the same graph, and that makes sense because they are the same equation. Okay, so what we're seeing here is that y equals 2x all squared, which we could think about as a dilation by half from the y-axis, is the same as y equals 4x squared, which is dilation by 4 from the x-axis. Now obviously that's not going to be the same for all functions. You can't say for every single function dilating by half from the y-axis is the same as dilating by 4 from the x-axis, because if I made this a cubic function, 2x all cubed isn't the same as 4 times x cubed, it's the same as 8 times x cubed. So in the case of the cubic, dilating by half from the y-axis would be the same as dilating by 8 from the x-axis. Okay, so it's not, we can't come up with a blanket rule, but the point is that for these functions we wouldn't think about these as y dilations, we would expand them out and think about them as x dilations, and therefore we haven't needed to think about this dilation from the y-axis before now. Let's see if we can generalize that a bit more. So we've just seen this happen here. So we know that f of 2x, which is a dilation by a factor of half from the y-axis, if the function is x squared, that is 2x all squared, which is the same as 4x squared, which is the same as 4 times f of x, so the same as dilating by a factor of 4 from the x-axis. If it is a cubic function, we dilate by half from the y-axis, so we f of 2x, that is 2x all cubed. Expanding that out, it is 8x cubed, which is 8 times the original function, 8 times f of x, so a dilation by a factor of 8 from the x-axis. If we dilate by a factor of half from the y-axis for the hyperbola, f of 2x becomes 1 over 2x, which we can also write as 1/2 times 1 on x, which is what we were doing in that previous lesson on hyperbolas. We were getting graphs like this and we were thinking about it this way so we could think about it as a dilation from the x-axis. Now actually in this case, half times 1 over x is just half times f of x, half times our original function. So in the case of the hyperbola, dilation by a factor of half from the y-axis is the same as dilation by a factor of half from the x-axis. Okay? But again, not true for all function types, just true for the hyperbola. If we have the truncus, 1 on x squared, dilating it by a factor of half from the y-axis is 1 on 2x all squared, which we can write as 1 on 4x squared, which we can write as 1/4 times 1 on x squared. So it is 1/4 times the original function. So dilating the truncus by a factor of half from the y-axis is the same as dilating the truncus by a factor of 1/4 from the x-axis. And lastly, our function, square root function, if we dilate the square root function by half from the y-axis, so f of 2x is square root of 2x in the case of the square root function, we can break that up by writing it as square root of 2 times square root of x. And so it is the same as root 2 times the original function, and so it's the same as dilating by root 2 from the x-axis. Now, rather than have to think about dilation factors that are surds, we would prefer to think about the dilation as being from the y-axis. So this is the first time where it starts to become necessary to think about dilating from the y-axis. Dilating from the y-axis is also going to be relevant with our exponential and log graphs later this semester, and in particular going to be relevant with our circular function graphs in semester 2. Okay, so again, it's an extra transformation we haven't had to think about until now, but we do need from now on. Okay, so now we have to broaden our understanding of our transformations so we're encompassing everything. Dilation from the x-axis or dilation from the y-axis, reflection in the x-axis or reflection in the y-axis, translations left or right, translations up or down. And we can do that by thinking about this. The really important thing is, again, we won't worry too much about this year, we'll try to give you nice things, but next year something you need to be really careful about is this, what's happening in here and how they interact with each other. So if you want to talk about the dilation and the reflection from the y-axis, you need to factor it out. So you've got brackets. So that's the dilation and reflection from the y-axis caused by n, and then you translate by that value to the left. For example, if we had square root of 2x plus 4, we would need to factor out that dilation factor because at the moment it's interfering with the translation left or right. We'd need to write it as 2 times x plus 2, so that then it is dilation by 1/2 from the y-axis, translation to the left by 2, not by 4. Okay, so it's really important that you are a bit careful about what's happening inside the function there. Okay, so we're putting all those things together that we know. When we sketch a square root graph, as I said to you earlier, the first thing I want you to think about is which of the 4 shapes have you got? Which direction is your graph going in? Are there no reflections, so it looks like the top left? Are we reflecting in the x-axis, so it looks like the top right graph? Are we reflecting in the y-axis, so it looks like this graph in the bottom left? Or are we reflecting in both axes, so it looks like this graph in the bottom right? Okay, so make that decision first, then think about anything. Then think about any translations, which is going to move this end point, which is a key feature of this square root graph, and then calculating your x and y intercepts will take into account any dilations. Okay, let's draw some graphs. Sorry, I know this is a biggish section, but it's important to introduce those 2 new transformations properly. So sketching the graph of y equals -3 root x. Okay, so we've got the negative out the front. That's a reflection in the x-axis. So that means my graph shape is this one, going this way. Okay, Then we've also got a dilation by 3 from the x-axis. Okay, so we don't have x and y intercepts here because our endpoint's not moving. Okay, so this endpoint's really key. That's what you want to get drawn on first, so you know where you're starting your graph from and then which direction you're drawing it in based on your reflections. So our endpoint's not moving, it's staying at 0, 0 because we're not doing any translations, and so therefore we only have the one intercept. So we're going to need another point on this graph, so we're going to need to think about subbing in a value. So for example, when x equals 1, nice easy point, y equals negative 3 times root 1, so that's just negative 3. So I'd mark the point 1, negative 3 on my graph. It gives the sense of dilation. Okay, so axes starting at 0, 0, 1, 1, 2, 3, so 1, negative 3, somewhere down here, and we're going to draw our square root graph in, heading off out this way. 1, negative 3, and 0, 0. So at least 2 points on your square root graph, including that end point. It's really important. Usually those 2 points will come from your intercepts. Usually you'll have 3 points, 2 intercepts plus your end point, but minimum 2 points. Okay, number 4. Sketch the graph of y equals half times the square root of negative x. Okay, so the half out the front is a dilation by half from the x-axis. Okay, we're familiar with those. Sticking a number out the front is just stretching from the x-axis, or in this case, squashing. The negative inside the square root is a reflection in the y-axis. Okay, so this time our graph shape's going out this way, and we've got that dilation by a half. So again, we're not moving where that end point is. Okay, that end point is still at the origin, so we don't have any other intercepts, so we need to mark a point. So again, this time, when x equals 1 is not relevant because the graph's not defined when x equals 1. So perhaps when x equals negative 1, y is going to be half square root of negative negative 1. So that's half times the square root of 1, which is just half. So we've got negative 1, 1 half would be the key point there. Okay, so again, axes, endpoint at the origin, negative 1, 1 half. Okay, and drawing in your square root graph. So again, make sure your graph doesn't dip down at the end, make sure it doesn't veer away, thinking about graph shape. Okay, so this point is, negative 1, 1 half. And we don't technically need to mark the origin, but there's not much else going on here, so I'm going to just label it while I'm there. Okay, so there's that graph. Right, number 5. Sketch the graph of the square root of x minus 3 plus 5. Okay, so no dilations and reflections here. We're subtracting 3 underneath the graph, which is a translation to the right by 3, and then we're adding 5 outside the square root function, so that is a translation up by 5. So this means that the end point of the graph is going to move. So the end point is going to go to 3, 5. Okay, again, we have no reflections here, so our shape is this, and that's going to go to the right by 3 and up by 5, so it now starts at 3, 5 and then goes up and to the right from there. Okay, so again, we're not going to cross the x-axis thinking about this shape, okay, because it's going to head off up here. So it's not going to cross the x or y axis, so we won't have any intercepts, so we need another point. So just sub a number in, okay. Sub in something that's going to give you a nice square number, so maybe, when x equals 4, for example, would give us y equals the square root of 4 minus 3, so that's square root of 1. So that's just 1 plus 5, which is 6. So it goes through the point 4, 6. You can pick another number, but try to avoid surds if you can. So maybe if the next square number is 9, so if you went with x equals 12, for example, you would have y equals 12 minus 3 plus 5, so that is square root of 9 plus 5, so 3 plus 5, which is 8. So you could have 12, 8. Up to you, okay? You don't need more than one, just pick a point. You can, however, point with surds in it, but it's sort of nicer just to choose one without. Okay, so we've got our graph. What do we need? 4, 6, and 3, 5. Okay, so let's go with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, so we've got, in fact, I'm just going to make that y scale a bit smaller, otherwise my whole graph's going to be off the screen. So remember, you don't need the same scale. 1, 2, 3, 4, 5, 6. You just need to be consistent along the axes in terms of your scale. So endpoint is at 3, 5, so 3, 5 up here. And my other point is at 4, 6. Probably should have made my y scale somewhere in between those two things, because now I've got a very flat square root graph in quite a big amount of space. Okay, so endpoint is important. It should be a solid closed circle. Again, we'll talk more about that in the next topic. We haven't talked properly about that, but a solid closed circle at your endpoint, so it's a clear finishing to the graph. It's not that your graph just stopped randomly in the middle of nowhere. It's a key point. Label it with its coordinates at the point. Please, I'm really not a fan of labeling 3 and 5 here, because if your point's not exactly at 3, which mine isn't, if I got a ruler out, then it's a bit ambiguous. Well, is that point actually at 3 if you haven't actually drawn it there? So just label it with the coordinates at the point, okay? And label your other point on the graph. Okay, number 6. Okay, so this is where we need to be careful. So remember, we talked about our general form, square root of n x minus h plus k. So we need to worry about this, which at the moment is a problem, okay? So we haven't got that n factored out, so we need to do that first. So this is square root of negative 2 times x plus 4. And then we've got that minus 1 outside the square root, which is your translation up or down. Okay, so the negative in under the square root, that's a reflection in the y-axis. Okay, remember the negative outside the square root, reflecting in the x-axis, under the square root, reflecting in the y-axis. So it goes to the left. We've got a dilation by reciprocal of 2, so half from the y-axis, so it's going to get squashed in. Again, dilations don't really affect how we draw the graph. It's going to be about where the points on the graph are. And then we're going to also be translating the graph to the left by 4, and translating down by 1. So these two things are going to move that end point. So that means that the end point of the graph is going to be at negative 4, negative 1. So we're going to be moving this graph across to the left by 4 and down by 1 and dilating it a bit, so it's going to head off out that way. So it is going to cross the x-axis, but it won't cross the y-axis. So thinking through your shape before you do your calculation so you know what you need to work out. So I'm going to have an x-intercept here that I need to find, same as every other graph type. Let y equal 0 to find your x-intercept. You can go back to the original unfactorized version if you want, doesn't matter. It's the same equation. Adding 1, squaring both sides, still gives you 1. Adding 8, and dividing by negative 2. So negative 9 on 2, or negative 4.5. Okay, so again, let's think about drawing in our graph. Okay, so we've got 1, 2, 3, 4, 5. Okay, negative 1. Might just make that slightly bigger actually, just to give us a bit of a graph. So 4, negative 1 is my, negative 4, negative 1 is my endpoint. So I'm going to mark that there. 4.5, negative 4.5 is my x-intercept, so that's going to be there. And so I'm going to draw my square root graph. Labeling my points, minus 9 on 2, 0 for my x-intercept, minus 4, minus 1 for my endpoint. At least 2 points drawn on my graph, all intercepts always marked. Okay, so there's the examples. I know that was a reasonably long section, but important to get those new transformations right. So some work for you to do from exercise 4C, sketching some graphs of square root functions.